Okay, so we'll continue with our lectures. As I told in this phase of the lectures, I'll be discussing more on the understanding concepts of the turbines and pumps. I've shown some videos in the previous classes, and we discussed those videos on Pelton wheel and Kaplan turbine. I hope you have a better understanding now. Henceforth, we'll be seeing videos on cavitation as I promised in the previous class, and also at the end of this class, if possible, we'll try also to cover some videos on pumps. I hope you don't have any doubts in the derivations and the numericals and some exercises in this units, turbines and pumps. We have already discussed the problems and shared few notes, and you may also find videos from Dr. R. Sridhar on the problems. So we'll start with the cavitation now. In the previous video, I've given you a task of and exploring what is cavitation. You must have seen it uh, in your life. I guarantee everyone have seen it, but you may not know what actually it is or what actually we call it. For an example, if you remember or if you try to just try to recollect, if you have seen a boat or a propeller of a boat, what happens there? You might have seen the movie Titanic, or even if you have traveled through some small boats, we have a propeller. And for example, in a motorboat, you have a propeller at the bottom, and when you start the engine, the propeller starts moving. What do you see? First of all, you hear some noise, some sound, and you then see some white bubbles or white froth on the water, and then it disappears. So what actually it is? So if you see in the micro level, it is nothing but generation of air bubbles, and when it breaks, it pops, and that sound is nothing but what you hear, the noise. So it's just a generation of air bubbles and bursting of those bubbles, popping of that, and the sound. So this is all cavitation. So what we are going to see is how it can damage your blades. So you don't think that it's just a simple phenomena, it won't affect. But just like a propeller, we also have our Kaplan turbine. So even we have a problem of cavitation in there. So that can affect the blades of your propeller or turbine. So what measures to take, how it occurs, what can be done, everything we'll study now, okay, by watching the video. You can always go and read. As I said, not much importance is given to this topic. Hardly a note can be asked for 4 marks on what is cavitation and what are the remedial measures to avoid cavitation or to prevent our blades from damage. So this is the type of question it may be asked. Today we'll see it in detail through the video. Okay, so this is the first video.
Welcome to e-learning in thermodynamics and fluid dynamics of our bachelor program in renewable energy and environmental technology. In this series, we are going over the phenomenon of cavitation in water and its consequences. What is cavitation? Cavitation is the rapid formation and collapse of vapor bubbles within a liquid. Such cavitation bubbles are formed mainly in locations within the liquid where the static pressure becomes smaller than a liquid's vapor pressure.
I hope you have studied what is a vapor pressure. I won't repeat it and waste time now. In fluid mechanics, I have studied this already.
The phase diagram of water shows if water is in its gaseous, liquid, or solid state, depending on temperature and pressure. The horizontal axis of a diagram represents temperature, while its vertical axis shows pressure. A vapor pressure curve is part of a phase diagram. It indicates at which pressures and temperatures water evaporates from liquid to vapor or condenses from vapor to liquid. At a constant pressure of 1 bar absolute, water in its solid state, which is ice, melts to liquid water at a temperature of 0 degrees Celsius. Keeping the pressure constant at 1 bar absolute, liquid water evaporates when the temperature is increased above 100 degrees Celsius. Evaporation of water is not only possible when the temperature is increased at a constant pressure. The other possibility is to keep the temperature constant and reduce the pressure below the vapor pressure. Water can evaporate and condensate at temperature.
So in short, what they are speaking here is what you have studied, or what according to your perception so far, water will freeze below 0 degrees and will boil or get vaporized after 100 degrees. So this is based on the temperature. But this plot also says that we can also play with its states, not with respect to temperature but also with the pressure. So as you can see here, the pressure, this is the temperature, so it goes from solid to liquid to gas. But also it depends on the pressure. If you increase the pressure, what happens? If you decrease the pressure, what happens? For example, in your household we use pressure cookers, right? Why do we use them? Anyone can think of this? Why do you use pressure cooker? The simple in from the answer from your mother will be like, just to save time. But what actually happens inside there? Yeah, the water will reach boiling point faster, right? Because you have increased the pressure. So you have increased the pressure inside there. So even at less this thing, it will vaporize, less temperature. Okay.
Below 100 degrees Celsius if the static pressure is low enough. This is exactly what happens when cavitation occurs. Bubbles of water vapor form when the pressure in a certain location decreases below the vapor pressure.
Now here you may say that, sir, the in the water the temperature is not 100 degrees, but still we can see bubbles there. So still the water is vaporizing. How? So it goes back to that diagram. So in that case, the temperature has not risen to 100, but we have increased the pressure. So even the temperature of, let's say, 20 or 30 degrees, if you increase the pressure, water can vaporize. So we can see bubbles. So this is what is happening here. Okay.
The vapor condensates back to liquid once the bubble has reached a location with a pressure above the vapor pressure. But how is it possible that the pressure becomes very low in certain areas of the fluid? Let's have a look at an example for illustration. If objects such as blades of a ship.
So this is the figure of a propeller of a ship. But in our case, we are studying Kaplan turbine. So if you remember, the shape of the Kaplan turbine is very much similar to the shape of a propeller of a ship.
The propeller are moved through water, there is a higher pressure on the side facing the flow and a lower pressure on the opposite side. On other edges exposed to the flow, low pressure can also lead to cavitation. The bubbles collapse as soon as they reach an environment with a pressure above the vapor pressure. When pumps circulate water through piping systems, cavitation can occur where the pressure is lowest.
Another example of cavitation we have is also in pumps. In unit number 5, we are studying pumps. But what happens inside the pipes due to changes of pressure? So even there cavitation can occur. So that will cause rusting of your pipes. So as an engineer, you have to design in such a way that there is the least cavitation occurring. And if not, you have to choose a material which can resist the cavitation phenomena.
At the inlet of pumps and in narrow pipe sections. If the pressure at the inlet of a pump is low and approaches the vapor pressure, cavitation can occur at the pump impeller as we have seen it at the ship propeller. The pump can deliver less water because the cavitation bubbles occupy a part of the cross-sections where the water should flow. Damage from collapsing vapor bubbles will be shown later. The same amount.
So this is a narrow section of a pipe. So we have a regular pipe, and when the section is narrowed at some joints, so how the cavitation will occur? You just look at the chain. The red indicates high pressure, and blue indicates low pressure.
Water per time flows through the pipe with a large cross-section as through the narrow cross-section. Therefore, the velocity is higher in the narrow part and the static pressure is lower. The pressure is especially low at the exposed edge at the inflow side of a narrow part. We show a detail of a phase diagram of water, which allows to analyze the situation in a narrow pipe section. The temperature of the flowing water can be 20 degrees Celsius.
Okay, we will not go into detail of this. If you want to go, or if you are interested in this phenomenon, you can always go and read some higher level textbooks and all. And if you choose a course for your masters after your engineering, which is related to this hydraulics, you can study it there in detail there. But at this point of time, what you have to understand here is the concept of cavitation, and the basics for that is the vapor pressure, the phase of the waters, and under what temperature and under what pressure. So if you know these basics, it is more than enough to explain the cavitation.
Absolute Pascal above the vapor is the low pressure at the exposed edge causes cavitation bubbles to form. At a pressure of 2,300 Pascal, a certain mass of water vapor requires over 50,000 times more volume than in its liquid state. The bubbles collapse as soon as they reach a region with a pressure above the vapor pressure. Because water from the vapor bubble occupies...
You can see from here the water vaporize here, form bubbles, and as soon as the pressure is increased, it will from the vapor pressure it will again become normal and it will burst it out. So this is the here which is the critical cross section inside a pipe. So here we need to be very careful.
50,000 times less volume after having condensed its liquid state. The collapse of each bubble is a spectacular event and emits pressure shocks. Pressure shocks from many collapses result in an audible noise very characteristic to cavitation. The sound used now in the video has been recorded in an experimental setup similar to the one in the animation. But how does it look like when cavitation bubbles are formed and collapse in detail? We can see the formation and the collapse of cavitation bubbles with a diameter of approximately 9 millimeters in slow motion. In real time, this process takes about 4 milliseconds, and it is a spectacular physical event. Because liquid water occupies many thousand times less volume than vapor, the bubble implodes. It first assumes a ring shape. Shock waves and a strong microjet are the result of a collapse. Let's go through the whole process again. If the local pressure decreases below the vapor pressure, water evaporates. A cavitation bubble is forming, is growing larger, and is transported with the flow to a region with a higher pressure. The bubble stops growing. If a local pressure exceeds the vapor pressure, vapor condenses, starting from the bubble's wall. Its surface starts to break down at its weakest spot. A microjet forms and pierces into the bubble's opposite surface. The bubble is now collapsing. The bubble becomes a torus and disintegrates further. The microjet continues to flow in the liquid and can hit a wall. Through its concentrated impact, even high-strength material can be damaged. The implosion releases energy in a very short time, concentrated.
So here the bursting of the bubbles is not as safe as it looks. So when there was a bubble, and once the pressure starts increasing above the vapor pressure, so this bubble will burst, and you can see on this side it will come diverge inside, and there is a small liquid jet which is coming out. This will attack the surface, and this has a very high power. It can also create some dents on a very thick metal, so you can imagine what uh, action it has. And if there are multiple and billions of bubbles, you can imagine what will happen to your plate. So this is very critical now.
In a very small spot. If a microjet hits a surface, it damages the material by a localized short-term overstraining. The material starts to evolve microcracks, and later material can break off.
One activity you can do is go and just look at some blades of a propeller of any pump or any uh, propeller of a small ship, a small motorboat, and just take a close look at that propeller. You can see some small dents. If they have painted, even the paint must have got some micro cracks. So this is all due to the cavitation.
We show a few examples of damage in pump impellers kindly provided by the Swiss pump manufacturer Herney. A brand new impeller to the left in comparison with an impeller having been continuously exposed to cavitation during 6 months, another impeller with damage from 12 months operation in cavitation, and one from 24 months. The new impeller shows the geometry as it should be under normal operation without cavitation. After 6 months of operation under cavitation, material has been eroded in the center of the wheel. The respective areas are highlighted with gray color. The impeller blades are undamaged. After a year of operation under cavitation, the damaged geometry has a different shape, and therefore the flow has a different pattern. The collapsing cavitation bubbles cause material break-off at the top edge of the blades. After 2 years, the blades have been eroded completely, which makes it impossible for the pump to function.
So this is where your maintenance part comes into picture. Like, so any mechanical things are not permanent. You always have to understand what are the phenomena acting in that component, and you have to take care of that. Some things, some phenomena are inevitable. You cannot avoid them, so you have to face them. Excuse me. As an engineer, your job is to minimize those damage, either by avoiding it as much as possible, or to design it in such a way that the life of it increases. So in this case, if you see, if there was no proper design, if the cavitation continues in the pump, in less than 2 years you have the pump completely dysfunctioning. Okay.
In this video, we have shown the basic mechanism leading to the formation of cavitation bubbles, which reduce the flow of water. We have also seen the spectacular collapse of cavitation bubbles, leading to noise and damage even to high-strength material. Systems have to be designed such that cavitation is avoided.
If a propeller spins quickly, it leaves a trail above the propeller.
So this is a video from National Geographic, and they are also explaining the cavitation, the vacuum pressure, the vapor pressure. Everything is explained in detail here. So have a good look at this video. You may also find this video on online on the National Geographic channel, or also on the YouTube. Okay.
Propeller spins quickly, it leaves a trail of bubbles. The propeller spins quickly, it leaves a trail of bubbles behind it. As the bubbles pop, they make a lot of noise. These bubbles are not filled with air, but with steam. The steam is produced by the seawater boiling. It is a well-known fact that water boils at 100 degrees centigrade. However, few people will know that at different pressures, the water will boil at different temperatures. If you increase the pressure, as in a pressure cooker for instance, then the boiling point of the water increases. Hence, the cooking is more efficient. Few people will know, however, that at reduced pressures, water will boil at lower temperatures. I have here a vacuum pump, and I'm going to turn on the vacuum. This flask here contains water, and we have it connected to a pressure gauge. The propeller spins quickly. It leaves a trail of bubbles behind it. As the bubbles pop, they make a lot of noise. These bubbles are not filled with air, but with steam. The steam is produced by the seawater boiling. It is a well-known fact that water boils at 100 degrees centigrade. However, few people will know that at different pressures, the water will boil at different temperatures. If you increase the pressure, as in a pressure cooker for instance, then the boiling point of the water increases. Hence, the cooking is more efficient. Few people will know, however, that at reduced pressures, water will boil at lower temperatures. I have here a vacuum pump, and I'm going to turn on the vacuum. This flask here contains water, and we have it connected to a pressure gauge, and we're reading at the moment approximately 15 pounds per square inch, which is 1 atmosphere. I turn on the pump. You notice the pressure dropping immediately, and as the pressure drops, as we approach zero, bubbles start to form, and the water starts to boil. So here we are at room temperature, but at a significantly reduced pressure, almost the complete vacuum. The water is now boiling. Water boiling at 20 degrees centigrade at almost 0 pounds per square inch, a remarkable phenomenon, sir. When a submarine's propeller turns quickly, an area of low pressure is created on the blades. This lowering of pressure causes the water to boil without heating up and produces bubbles of steam. This is called cavitation.
Formation of those bubbles is dependent on how fast we rotate our propeller. So the faster we go, the more risk we are for cavitation.
The Pennsylvania's propeller design is a closely guarded secret, but the basic principles of a quiet running propeller are known. Cavitation only occurs when a propeller spins quickly. Slowing the propeller down reduces cavitation and therefore noise, but slowing the propeller also reduces a submarine's thrust. To overcome this problem, the Pennsylvania's engineers developed a unique propeller with 4 additional specially shaped blades. These generate large amounts of thrust, but at much lower speeds. This way, the Pennsylvania produces almost no cavitation or propeller noise. She is a silent predator of the deep.
So here was a nice example of a Pennsylvanian submarine. If see, this phenomenon is as we discussed, it is inevitable. So the sound is also inevitable, and in some cases, like in submarines, we don't want sound because there are also other submarines inside the sea, and we don't want them to hear us. So in that case, we should have less sound. So less sound means less cavitation. So how to reduce that cavitation they have designed. So instead of having 2 or 3 propellers, they have designed a propeller, a special kind of design. As they said, it's a secret, they'll not disclose, and it will give you more thrust even at very less speeds of that, so you'll have less cavitation. So you can see it's a very big field of fluid mechanics of this cavitation. If you have interest, you can do some masters and you can end up doing some designs of some propellers or even some turbines in civil engineering, which will be helpful to you. Uh, Further, you may have to study computational fluid mechanics. So with this, we almost end our hydraulics part. In the last semester, we studied fluid mechanics, and here we studied hydraulics and hydraulic machines. Henceforth, you won't be dealing with fluid mechanics. You will be just studying the applications. But if you're planning to do masters or some other higher studies, the extension of this subject is very huge, and amongst it we have a subject called computational fluid mechanics, CFT. You can, if you have some mechanical students, engineering friends, you can ask them. They may study this also. So computational fluid dynamics is a very vast topic. So you have to in detail program or model this phenomenons, and to you do that you may have to learn some mathematics, some numerical methods, and even there are some softwares available. So if you have some interest in this, you can always go ahead and study this. Okay. So now we have almost finished discussing the videos on unit number 4. So I'll repeat again. So we have spent a lot of time in understanding the basics of this, the designs, the flow, the problems, the derivation. It's already discussed, and the notes have been shared, so you can prepare for the final exam. In this last part now, unit number 5, which is already covered by Namrata, Professor Namrata, she is discussing few problems and some derivations. What I will discuss is we'll watch some videos on pumps, different type of pumps and how they are put in series, parallel, and their components and how they work in detail using some videos. Another thing which is a kind of debate over here is, like in the when there were no videos and there were no 3D animations, those time the students used to kind of visualize and imagine just from a 2D diagram. So a 2D diagram was available in the textbooks, and just by reading the description, students used to visualize. In this case, we are showing you some videos, and we are not allowing you to visualize. We are just trying to see it and try to understand it. But as a good practice, what I would suggest you is to stop this video now or pause it. Look at some 2D diagrams of pumps. Okay, look at some 2D diagrams of the pumps. Read its description and its working, not the derivation part or not any mathematics part. Just try to read its description and its working, the components, and try to imagine how much will be the size of it, how it's the shape, how it will work in 3D, what actually is happening. So how the cross section of that varies. So everything you try to just analyze in detail. Okay, so after that you can come back to this video, and then we can discuss on the videos on pumps.
Centrifugal pumps. Talking about the pumps, we always come across the centrifugal pumps. Their uses can be seen.
So even in your syllabus we have one type of pump which is centrifugal pump, which is very commonly used pump.
In water, sewage, petroleum, and petrochemical pumping.
Some pumps are not submergible and some are submergible. You might have seen some pumps which are installed into your tanks, water tanks in the basement. So those are submersible pumps. Some are not submersible pumps. You have to just put some inlet of water to it. Okay.
Now the question is, what is centrifugal pump? A centrifugal pump converts mechanical energy from a motor to the energy of a moving fluid. A portion of the energy goes into kinetic energy of the fluid motion, and some into potential energy, represented by fluid pressure or by lifting the fluid against gravity to a higher altitude. Or we can say a centrifugal pump is a rotating machine in which flow and pressure are generated dynamically.
Here, I just remember one course activity. So to make this pumps more interesting, you can go, like every one of you or most of you will have a pump in your house. It may be in your industry, in your house, in the basement, or in your farms, in agriculture. Everywhere you'll have some pumps. So here you can do one small activity. Go out, look at the pump, just try to see who is the manufacturer of the pump, what are the specifications of the pump, how what is the HP of that pump. Generally you might have heard half HP, 1, 2, what this number is very common in the market. So you can just try to find out what is the HP of that pump. So how much meters it can lift the water. For example, how much tall is your building. So for that, how much HP pump you are using. So these all things are very helpful in the practical life. Tomorrow, if someone asks you that I have a G plus 4 stories building, so what HP pump should I buy? Are you able to answer it? You just ask this question to yourself. So this is the way you should think of. In some agricultural field, they might ask you, my farm from is like some meters or some kilometers away from the river. From there I have to pump the water to my field. So what is the size of the pipe, what HP pump you should install. If the farmer asks you, in some or the other way you should be able to answer his question. You should not over design him. For example, if there is a solution, it is required 1 HP pump. You shouldn't over design and tell him that you just install 2 HP pumps. So this is also not good. It's not economical. Okay.
Now let's understand the principle of centrifugal pump. The centrifugal pump creates an increase in pressure by transferring mechanical energy from the motor to the fluid through the rotating impeller. Fluid enters the pump through the eye of the impeller, which rotates at high speed. The fluid is accelerated radially outward from the pump casing. A vacuum is created in the impeller eye that continually draws more fluid into the pump. The centrifugal force hereby increases the fluid velocity, and consequently also the kinetic energy is transformed into pressure, which in turn lifts the fluid against gravity. The energy created by the pump is kinetic energy, according to the Bernoulli's equation. Now let us see the important components of centrifugal pump. Impeller. It is a wheel or rotor which is provided with a series of backward curved blades or vanes. It is mounted on the shaft, which is coupled to an external source of energy which imparts the required energy to the impeller, thereby making it to rotate. Casing. It is an airtight chamber which surrounds the impeller. It is similar to the casing of a reaction turbine. Suction pipe. It is a pipe which is connected at its upper end to the inlet of the pump, or to the center of which is commonly known as eye. The lower end of the suction pipe is dipped into liquid in a suction tank or a sump, from which the liquid is to be pumped or lifted up. The lower end of the suction pipe is fitted with a foot valve and strainer. Delivery pipe. It is a pipe which is connected at its lower end to the pump, and it delivers the liquid to the required height.
So you can see there are around more than 5 components of a pump. So each part has a very important role to play.
Just near the outlet of the pump on the delivery pipe, a delivery valve is provided. Now let us move to the working of the centrifugal pump. The first step in the operation of a centrifugal pump is priming.
I don't know how many of you have came across this word priming. How many of you? Yeah, if you have operated some pumps and if it is not used for longer period of time, or sometimes you may have to do that priming process. Now what is that priming process? We'll look at it. Okay.
Priming is the operation in which the suction pipe, casing of the pump, and a portion of the delivery pipe up to the delivery valve are completely filled with liquid.
In one or the other case, you have to fill water inside the pump. So in a common layman term, there will be a small opening on the top. You just open that screw and completely fill that with water. This is what you have to do when you do priming. Okay.
Which is to be pumped, so that all the air from this portion of the pump is driven out and no air pocket is left. After pump is primed, the delivery valve is still kept closed and the electric motor is started to rotate the impeller. The delivery valve is kept closed in order to reduce the starting torque for the motor. The rotation of the impeller in the casing full of liquid produces a forced vortex which imparts a centrifugal head to the liquid and thus results in a centrifugal head and thus results in an increase of pressure throughout the liquid mass. The increase of pressure at any point is proportional to the square of the angular velocity and the distance of the point from the axis of rotation. Thus, if the speed of rotation of the impeller of the pump is sufficiently high, the pressure in the liquid surrounding the impeller is considerably increased. When the delivery valve is opened, the liquid is made to flow in an outward radial direction, thereby leaving the vanes of the impeller at the outer circumference with high velocity and pressure. At the eye of the impeller, due to the centrifugal action, a partial vacuum is created. This causes the liquid from the sump, which is at atmospheric pressure, to rush through the suction pipe to the eye of the impeller. As the liquid flows through the rotating impeller, it receives energy from the vanes, which results in an increase in both pressure and velocity energy. The shape of the casing is such that the leaving liquid flows through a passage of gradually expanded area. This change in shape uniforms the kinetic energy of the fluid.
If you have seen some images in the books, you may find that this cross-sectional area will increase. So from here, as it goes on the top, you may see a change in cross-sectional area. We have another video.
Centrifugal pumps are the most preferred pumping devices in the hydraulic water stream in reducing exit flow. Current impeller type is enclosed. Semi-open and open impellers are all.
We'll just watch this video. It's very descriptive, and the actual pumps you can see in the practical case.
I'm Adam. This is the Machine Tech video blog, and today I'd like to talk to you a little bit about the different types of centrifugal pumps. When it comes to pumps, most operators only care about inputs and outputs. How much pressure does the pump generate? How much flow does it deliver? how much power is required to run it. But maintenance people need to know a few more details about the inner workings of these machines if we're going to be on the hook to keep them in good running order. We don't have time to cover the specifics of centrifugal pump operational theory here, but it was the topic of a previous video. Just as a refresher, centrifugal pumps get their name from the way they impart energy to fluid. When fluid enters the pump, it comes into contact with the rotating impeller and is thrown outward by centrifugal force. It travels through a specially shaped chamber called a volute and exits the pump at the discharge outlet. All centrifugal pumps share this basic operating principle, but there are a few possible variations among them. There are 5 primary design elements to consider: impeller construction, bearing configuration, orientation, driver mounting method, and the number of stages.
For our syllabus, if you have understood, we have this as an important aspect, number of stages. Okay. Rest is all mechanical part. Will not go into detail, but the stages, the single or the parallel. So these are the important things you must know.
There are a few special designs as well, but those will have to wait for their own videos. There are 3 types of impeller: open, semi-closed, and closed. The simplest impeller construction is the open impeller, which consists of nothing more than a few curved blade-like vanes equally spaced around a hub on the rotating pump shaft. Large, unrestricted fluid pathways allow this type of impeller to pump fluid containing mud, leaves, twigs, sand, sludge, spray paint, cabs, dead birds, you name it. And that makes them ideal for trash pumps or this pump, which actually came out of a wastewater treatment plant where it was pumping raw sewage. It was necessary to handle gritty slurries with soft solids. And it even has special chopper blades just ahead of the impeller to help break down very large solids. Ooh. If the vanes are mounted on a backing plate called a shroud, then the impeller is a semi-closed impeller. And if the vanes are sandwiched between 2 shrouds, then it's a closed impeller. Closed impellers are more efficient than either semi-closed or open impellers because the fluid is directed through very well-defined pathways. That means that more of the fluid is pumped out into the system and less of it is just recirculated around and around and around inside of the pump. Of course, the trade-off is that they can very easily get clogged with debris. Whichever style of impeller is used in a pump.
Basically, the impeller, you have to choose it according to the use of your pump. Sometimes you may just have to pump clean water, some chemicals. Sometimes you have to also use some pumps for like pumping concrete or for your sewage pipes or also wastewater treatment plants. So in such cases you may have some particles inside there. So depending on that, you have to design or choose a pump which is suitable for pumping.
It's mounted on a rotating shaft and needs to be supported by bearings inside of the casing in one of 2 ways, either overhung or between bearings. In an overhung configuration, the impeller is cantilevered on to the other side and discharge piping at 90 degrees to one another, with the center overhung suction abundant in texture rising from. During operation, there's a zone of low pressure at the suction eye where fluid first enters the impeller, and a zone of high pressure at the outside rim of the impeller where the energized fluid is released into the volute chamber. This high-pressure fluid also has a leak path to the backside of semi-closed and closed impellers, which totally throws off the balance of pressure. The net effect is a constant axial force, or thrust load, pushing the impeller toward the suction inlet of the pump. You can compensate for this effect a little bit by installing beefier bearings capable of handling thrust loads, or drilling holes through the impeller shroud to allow for some pressure equalization. But neither of these are true fixes for the problem. A more effective solution is presented if the impeller is supported by bearings on both sides, called a between bearings configuration. Not only does support the manufacturing sizes and styles, but one characteristic common to all of them is that they require proper alignment of the shafts, and that can be a very finicky process indeed.
So in like a bigger volumes, you have to have big pumps, and the motor, the shaft, everything has to be aligned. Even for case in our institute, we have sewage treatment plant. So we have a rotator there, and if possible, you can go and visit there. So alignment is a very important thing over here. Even if it is slightly disaligned, you may have some big problems occurring over there. So this is what I'm explaining here. Alignment is very important. Even though it's not there in a syllabus, but this is just an extra understanding.
To help facilitate and maintain machine alignment, the pump and driver are mounted on a common base plate, or in the case of units oriented vertically, the driver is mounted above the pump on a structural support called a C-frame. This type of pump and driver unit is said to be frame mounted. For large pumps, frame mounted second off the pump and its peller in the extra procedure, and the driver components are supported on the same shaft just by the bearings in the driver. This mounting method is really only appropriate for small and medium-sized end suction pumps. Finally, a pump can be classified by how many stages it has. Most pumps...
I would like to draw your attention here. This is very important part as per our syllabus, so you can have a close look at it.
Have one stage with a single impeller and a single volute chamber. However, some pumps have additional stages connected in series to help boost the pump's discharge pressure. The idea is that the first impeller adds energy to the fluid and then feeds it into the next impeller, which adds more energy to the fluid, then feeds it to the next impeller, and so on and so forth until the fluid is eventually discharged into the system. Well, there's your introduction to the different classifications used for centrifugal pumps: impeller construction, bearing configuration, orientation, driver mounting method, and the number of stages. And that's it for today from the Machine Tech video blog. I hope you learned something.
Okay, so this is enough.
Centrifugal pumps are most commonly used turbo machinery.
We have seen enough videos on these pumps now. I hope you have learned something extra from your books, and you have got a nice overview of this. Any doubts you have, you can always discuss again. Probably we'll make more videos on this turbines and pumps. Professor Namrata, as I said before, we'll be discussing on the problems and the numericals. So you have a lot of material now. Any doubts, you can always mail us or contact us. We'll be there to help you. Okay, thank you.